Hello class, here we are again, and we're back to the fourth part of this section on radius and convergence testing. And what we're going to do is we're going to talk about how we use a ratio test to find out if our series converges. So let's start off with what the ratio test is. Again, as the definition says, we have the limit as n goes to infinity, and what we compare is the ratio of our next term divided by the term right behind it, and we want to see what value that reaches. Now, if L is less than 0, we have convergence. If L is greater than 0, we have divergence. And if L is equal to 1, I'm sorry, I want to go back and rephrase this. If L is less than 1, we have convergence. Greater than 1, we have divergence. And equal to 1, we have we need to do more work because it's inconclusive. So I'm going to pause and put an example up, and then we'll get started again. So here's our first example. Our first example is show that that series converges for all x. So we're going to do the ratio test, and we're going to consider absolute convergence because we don't want to be dealing with negatives or alternating signs. So we'll start off by setting up the limit as n goes to infinity, and remember it's got to be a to the n plus 1 over a to the n, and what we'll get for that is the limit divided by now we have a compound fraction, and what we want to do is change this into multiplying the numerator by the reciprocal of the denominator. So we'll just rewrite this as the absolute value, and we'll multiply by n factorial in the numerator over x to the n in the denominator. Now, we like to group, and when we evaluate these limits, the n terms with the n terms, because that tends to help. And the x terms with the x terms. So that would be x, the absolute value of x to the n plus 1 over the absolute value of x to the n. Now, some things are going to cancel out. For instance, we're going to end up getting n factorial divided by n plus 1 factorial can be rewritten as n plus 1 times n factorial. It's a property of factorials. And the second term is going to be the absolute value of x times the absolute value of x to the n over the absolute value of x to the n. So this is going to cancel out with that, and now we are left with the limit as n goes to infinity, n factorial, 1 over n plus 1 times the absolute value of x. Well, if you notice with this limit, it's based on n. What that means is the absolute value of x can be moved out in front, and now we're just simply evaluating the limit as n goes to infinity. And what you should notice is that no matter what x is, this limit is going to head to 0. So the fact that x had no bearing on the problem means that the radius of convergence was infinite. Let's look at another example. Let's look at, for example, if we have the sum of n factorial times x to the n. We want to check that. So we'll check for absolute convergence using the ratio test. So we'll rewrite it as the limit as a to the n plus 1 over a to the n is going to infinity. So we're going to just rewrite that as n plus 1 factorial. The absolute value of x to the n plus 1 divided by n factorial over the absolute value of x to the n. We're going to evaluate the limit as n goes to infinity, and we'll do our factorial algebra on this again. Now in the numerator, we're going to have n plus 1 times n factorial all over n factorial. We're going to have x, the absolute value of x, times the absolute value of x to the n all over x to the n. And in this case, after we make our cancellations and reevaluate the limit, we have, as n goes to infinity, we have n plus 1, and our absolute value of x comes out in front of the integral. in front of the limit. And as you can see here, it doesn't matter what x is, it just tells us that the limit is going to go to an infinite value times x. So in this case, this series will only converge for x equaling 0. And that's really just convergence at a point. That radius of convergence would equal 0, because we only get convergence at one point, and that's when x equals 0. Let's look at one more example using the ratio test. In this example, I'm going to do the summation of n squared over e to the n. And we want to see when n starts out at 1 and goes to infinity, what happens to this series? Does it converge or diverge? So we will use the ratio test, and we'll check the limit as n goes to infinity of n plus 1 squared over e to the n plus 1 divided by e to the n n squared over e to the n. Remember, before we evaluate the limit, let's just simplify the fraction. So right here you can see I expanded my n plus 1 squared, and I rewrote it as multiplying by the reciprocal. And now when I check out the limit, I'm going to cancel out. I have n squared plus 2n plus 1 all over n squared. That's the limit as n goes to infinity. And this term simplifies to just being 1 over e. So that 1 over e really has nothing to do with n. So that can come out of the limit as a constant. And now I'm going to use L'Hopital's rule, because I have an indeterminate, not indeterminate form, I have a indeterminate form, because when I try to plug in the limit, I get infinity over infinity. So I'm going to use L'Hopital's rule, and that'll tell me to do the limit as n goes to infinity of 2n plus 2 all over 2n. In this case, I take the derivative and I get an indeterminate form again. So I'm going to do L'Hopital's rule one more time. And I'm going to get 2 over 2, which is not an indeterminate form. And I get an amount of 1 over e times 1. And what this means is that my limit is less than 1. That's less than 1 over e. And because the limit is less than 1, we have convergence. I hope these examples have helped with understanding how to use the ratio test, and we will definitely have some more problems to work on with this.